So our first main theorem of the course is Cauchy's theorem. It says that if P is a prime that divides the size of your finite group, then there must be an element in your group that has order P. So a to the P power is the identity. We're going to prove this in almost the exact same way we saw group actions in our last example. So here's the proof. I'm going to define a set X. X is the set of all P tuples. So A0, A1, up to AP minus 1, where each element in my P tuple is in my group. And I'm going to add the condition that when I multiply all the elements together in this order, I get the identity. I can act on the set X by ZP. So ZP acts on X by rotation. For instance, 1 plus one of these tuples will rotate this tuple to the right. Since 1 is a generator for ZP, once I tell you what happens to 1, you know how every other element in ZP acts on this. It rotates it 2 or 3 times and so on. Did I actually get an element in X back when I shifted everything to the right? Well, if you look at this condition on the set X, you could think of it as these two elements in the group, A0 and then the product of the remaining elements. These two elements are inverses. So if I put this A0 term in the back, then multiplying everything together just gives me the product of these two inverses in the other order. So I still get the identity back. So I do indeed get back something at X. It is a valid group action. So Burnside's lemma tells us the number of orbits. It's equal to 1 over the size of the group times the sum over all elements in the group, where I look at the sizes of the fixed point sets. So the size of the group ZP is P. Then I'm going to add all the sizes of these fixed point sets. Okay. 0 is the identity element in ZP. It doesn't affect your tuple. So 0 plus your tuple unchanges your tuple, meaning the fixed point set is everything in X. So like our previous example, I have a bunch of free choices for the terms in my tuple except for 1. What I mean by that is I could pick A1, A2, A3 up to AP minus 1 freely, but if I pick those elements in G, my choice for A0 is predetermined. It has to be the inverse to the product of my other choices. So I have P minus 1 free choices of anything in the group, and after I make those choices, A0 is dictated. I can't pick that one. It has to be the inverse. So the size of the set X is the number of elements in the group to the P minus 1 power. Now, the fixed point sets, what's X1? So X1 contains all tuples that are the same after I rotate. So that means my set X1 has to be everything of the form AAAAA, every element in my tuple the same, And it has to satisfy the condition that a to the p power is the identity. If you think about it for a second, that's also the same as the set x2. This is the same as the set x2. Why? The tuples that are the same after I rotate twice cyclically are those tuples of the form AAAAA. 2 is a generator for ZP. So if I cyclically shift 2 at a time, I'll hit every coordinate in my tuple. So that's actually x2. It's really all of these sets. They're all the same. So I'm going to group all these together and write this as p minus 1 times the size of x1. Now, p divides the size of the group. So this term, this is divisible by p. The number of orbits has to be a whole number. So in order for this to be a whole number, x1 must be divisible by p. The whole term has to be divisible by p. This piece is, so therefore this piece also has to be divisible by p. So in other words, p divides the size of x1. Now x1 is not 0. The size of x1 is not 0 because the identity element satisfies this condition. So there's at least one element in x1. It's the identity element. And since a prime divides x1, the size of x1 has to be at least p. Why? P divides it and is not 0, so the size has to be bigger than or equal to p. So therefore, x1 is non-empty. There's 2 elements in it at least, so there's another element A in the group that has order E. So there is an A in the group with order P.